Math 2415, Chapter 10, Vectors in the Geometry of Space, Section 2, Vectors. Video 3, Component Form of Vectors. Before we jump into component form of vectors, there is one special vector that I neglected to mention in the previous videos. And that vector is the zero vector, denoted as a 0 with a vector bar over it, or if you can type in bold, a bold 0. What do you think the zero vector does? What do you think its magnitude is? Well, the magnitude of the zero vector is 0. It's the vector that has no magnitude. So if you think about what that means in terms of displacement, if I start at a point and tell you that I need you to travel 0 units, it does not matter which direction we travel in, we're not going anywhere. The zero vector is a single point. The magnitude is 0, that's how long it is, and it has no direction. Or you could say it has any direction because no matter which way I face, if I walk 0, I'm not moving anywhere. So the zero vector is a thing, and it's something that I wanted to mention earlier. And in the context of scalar multiplication, if your scalar is 0, then your scalar product is 0. Or any scalar multiple of the zero vector is also 0. These things will be written down in a couple of videos when we get to properties of vectors. But let's talk about component form of vectors. So far we've looked at vectors geometrically as arrows illustrating displacement from one point to another. But in order to do calculus, we need to be able to do algebra. And in order to do algebra, we need numbers to represent generically as variables. And so far, the only numbers we've seen have been in the form of coordinates representing initial and terminal points of vectors. You may remember these two vectors from the first video when I drew a vector with initial point A at 1, 3 and terminal point B at 1, 4, 5, representing that vector as AB, and said that it's the same vector as this one with an initial point at the origin and a terminal point at 3, 2. I argued that you could check the magnitudes by using the distance formula and check the directions by calculating slopes, and everything would match up. But there's a much easier way to say these vectors are equal, and that's to calculate what's known as their component form. Loosely speaking, the component form is almost describing the slope by calculating the rise and the run from one point to another. For example, if I were to calculate the slope of line segment AB, I would calculate the run, which would be the difference in the x-coordinates, and the rise, which would be the difference in the y-coordinates. The difference in the x-coordinates is 4 minus 1, which is equal to 3, and the difference in the y-coordinates is 5 minus 3, which is equal to 2. To represent the fact that the displacement was 3 in the x direction and 2 in the y direction, we can write vector AB as what looks like an ordered pair, but instead of being in parentheses, we could write it in pointy parentheses and say 3, 2, meaning that we were displaced 3 in the x direction, 2 in the y direction. Now, you may have seen vectors written differently like this, and this is a perfectly acceptable way of writing the vector 3, 2. That means go 3 in the x direction and 2 in the y direction. You can write a vector as what's called a column matrix. Matrix being a rectangular array of numbers, column meaning one column. But for our purposes, we'll be using this notation when we write our vectors in component form. Although in some classes you need to fluidly be able to say that these are the same object. They're both the vectors saying go over 3 and up 2. Speaking of going over 3 and up 2, if we went to the second vector and calculated its run and its rise, excuse me, let me get a drink, you'd find out that it has the same run and rise as vector AB. 3 minus 0, excuse me, 3 minus 0 is 3. 3 minus 0 is 3. 2 minus 0 is 2. So vector OC in terms of components is also 3, 2, which is further confirmation that these two vectors were the same because their components were equal. In fact, that is the definition of equal vectors in component form. Two vectors in component forms are equal if and only if their corresponding components are equal. Let's generalize this and then take it to 3 dimensions. By generalize, I mean what formula could we set up to calculate the vector in component form that has a certain initial point and a certain terminal point? It's not really that hard to do. The way you generalize something is you remove the specific values and then you replace them with generic values, also known as variables. Let's say that we have the point, well, let's just pose a question. What is the vector in component form, comma, with an initial point let's call that initial point, I want to be consistent with the author, let's call that initial point x1 comma y1 and terminal point x2 comma y2. So this is asking this question generically. Specifically, we said 1 comma 3, 4 comma 5, or 0 comma 0, 3 comma 2. Generically, x1 comma y1, x2 comma y2. And the answer is pretty easy. This isn't really a formula. It's more of an idea. Just ask yourself how we calculated the component form over there. Well, we took the terminal points x and subtracted the initial points x, x2 minus x1. And we did the same thing for the y's, y2 minus y1. So it's real easy to come up with the component form of a vector if you know the coordinates of its initial point and its terminal point. Just remember, it's always terminal minus initial. And the same thing holds in 3 dimensions. If we were in R3, then our initial point would have 3 coordinates. Let's say x1, y1, z1. And I don't think I said this in class the other day, but when I write my z's, I put a line through them so you know it's not the number 2. If our terminal point was x2, y2, z2, then the vector in component form would be difference in the x-coordinates. It's always terminal minus initial, x2 minus x1, comma, difference in the y-coordinates, y2 minus y1, and then difference in the z-coordinates, z2 minus z1. And although we can't represent them easily visually and physically, we could do this in 4, 5, or as many dimensions as we want. We would just have ordered 4 sums, ordered 5 sums, ordered 6 sums, whatever you want to call them, and to find the vector connecting them, we would just keep subtracting corresponding coordinates. So it's really not that hard to calculate component form for a vector. Just remember that what each number in component form represents is a displacement in a certain direction. So for example, if we had the vector 1, -3, 2 in space, then this means wherever we start, we would go 1 in the x direction, -3 in the y direction, 2 in the z direction. That would be the terminal point, and when we connect them, that would be our vector. In fact, if I wanted to draw this vector, the vector is independent of where it begins. It only depends on its magnitude and direction. So if I wanted to sketch that vector, I can choose the initial point of my choice. When you're drawing a vector, just to illustrate its magnitude and direction and have the freedom to choose the initial point that you want, I would choose the origin. Makes sense. Origin, 1 in the x direction, so 1 this way. -3 in the y direction, so that would be -3 this way. And then 2 in the x direction, so up 2. And I'm trying to draw each arrow to represent 1 unit in each direction. If we connected the initial point at the origin by choice to the terminal point, which seems to be at the point 1, -3, 2, then this vector would be 1, -3, 2. So in that sense, we can almost talk about points in space as vector, because this point by itself is 1, -3, 2, but the vector 1, -3, 2 is the vector that initiates at the origin and terminates at that point. As we move forward throughout this class, you'll need to be able to easily go back and forth between this ordered triple represents a single point in space. Its corresponding vector represents the vector that initiates at the origin and terminates at that point. But keep in mind that this is not the only place this vector lives. I can pick up this vector and move it wherever I want. As long as I don't change its magnitude or direction, it's still the same vector it was before. It's just at a different location. But if you put it in, I guess we could say standard position, you can initiate it from the origin, just connect it to the corresponding ordered triple, and boom, you've got your vector. I'm sure there's something I'm missing here. That was too easy. No, that's good.